Welcome everyone, good afternoon. It looks from the title we're about to learn that the cosmos might be simpler than we all thought. That's spectacular news. And to tell us about it, we have Professor Neil Turok. He's the inaugural Higgs chair, I should say, of theoretical physics at the University of Edinburgh. He's a world-leading expert in cosmology. Before moving to Scotland, he was the director of the Perimeter Institute in Canada between 2008 and 19, I believe. And before that, he was in Cambridge, and before that at Princeton. Neil is also well known for having started great activities in Africa. Being born, I guess, in South Africa, right? He founded the African Institute for Mathematical Sciences, AIMS, at Cape Town, and then expanded to 6 different locations. I guess it started in 2003, and then by now it's 6 different locations, which is a major center for young people to be trained. So with that, without further ado, please join me in welcoming Neil to the stage.
Well, it's a great pleasure to be here. Thank you for the invitation. There's several friends of mine in the audience, so lovely to visit Stockholm. I'm going to tell you a little bit about a personal journey in theoretical physics, which I hope even those of you who don't work in cosmology will find interesting. Essentially, the last 40 years of so-called fundamental theoretical physics have not been that fruitful. Okay? Few people will admit that. But it came home to me very forcibly because I was director of Perimeter Institute, which is now probably the largest center in the world for so-called fundamental theoretical physics. And I was responsible for the strategy. Which fields do we invest in? Which fields of physics are going to teach us about things on a par with Maxwell and Dirac and Einstein? How are we going to make the next step forward? So I had to look very critically at all of these different fields and try to judge where progress was likely to come from. And that examination of the whole field actually convinced me that we'd all been on the wrong track, okay, ever since I entered the field. And we had pursuing a certain strategy which was looking for unification by adding more and more ingredients, okay? And anybody knows the worst thing you can do if you're building a model of some phenomenon is to add more and more parameters and convince yourself that it's all working, when in fact you're just, you're doing nothing more than adding parameters. So I think the field has had a whole number of fashions and crazes, and for those of you who watch cosmology from the outside, it must be incredibly confusing, because you see all kinds of claims. There's a multiverse, there's extra dimensions of space, and there's strings floating around, and all kinds of crazy ideas. And I guess most people who think critically just dismiss it all as nonsense. But we take this nonsense very seriously. And so within this field, I have recently, and this is only in the last 5 or 10 years, come to the point of view that actually we should be looking for simpler, more economical, and more predictive theories. And the thing that's taught us that is nature itself. When we look at the universe, and we look at we have fantastic observations now, and they are pointing, as Ariel said, towards incredible simplicity and economy in the laws of nature, not at wild chaos with all kinds of crazy things happening, quite the opposite. And it's the same both on very large scales and on very small scales. Everybody was surprised, or most people were surprised. We built the biggest experiment ever in the history of humankind, the Large Hadron Collider. And it found the Higgs boson, which was predicted 50 years earlier, but nothing else. Okay, and so again, surprising economy and simplicity. So I take this extremely seriously. In my own work, I've really tried to go back to the fundamentals and see, can we solve the puzzles about the universe with the absolute minimum of assumptions and ingredients? And this line of inquiry is very difficult. Essentially, you're tying your hands and saying, I'm not going to just introduce another particle or field or parameter. But in the last few years, it's begun to yield some fruit, namely some real predictions, which are very surprising and seem to agree with what we see. So that's what I'll talk about. So the work I'm going to describe is, most of it is with this person, Latham Boyle, who was my colleague at Perimeter, but he's now moving to Edinburgh. So we'll be together next year, and a couple of students. So this is the current consensus in cosmology, and I want to warn you that what I will be explaining is not the current consensus. Okay? This is, if you meet a cosmologist on the street, this is what they will typically tell you. Okay? That we live about 13.7 billion years after the Big Bang. And if we go back to about 380,000 years after the Big Bang, that's when the universe became opaque to light. It was very dense, very hot, and full of hot plasma. So when we look out, this is what we see, is this hot plasma surrounding us, and we see it as it was 380,000 years after the Big Bang. What happened before that? Well, most cosmologists, and this is the dominant paradigm, will tell you that the very early universe underwent a period of exponential expansion called inflation. And this inflation, this phase of inflation, is supposed to explain why the universe is so large and so smooth and uniform and the same in every direction. Okay, so it's like a great blowing up of the universe. So that if it was lumpy initially, those lumps would all be spread out and made uniform. This inflation had a side effect that through quantum mechanics, the quantum mechanical uncertainty in the early universe led to slight uniformities, non-uniformities, which we would see in the sky, and many people thought this theory must be right because it not only explains why the universe is big and smooth, it also explains the small variations in density which gave rise to galaxies and stars and all the interesting structure. So this is the dominant paradigm in the field for the last 40 years. The problem with it is twofold. One, this type of inflation is very arbitrary. There are many, many different models. There's about 10,000 models of inflation in the literature. You can blow up the universe in millions of different ways and with the same result. This blowing up also has the consequence that different parts of the universe would ultimately end up very different. And that promoted the idea of a multiverse, that we happen to be in this type of universe, but somewhere else, exponentially far away, there's another completely different universe. It also doesn't really deal with the beginning. I mean, the most paradoxical thing about the universe is that everything we can see seems to have, if we just extrapolate back the known laws of physics, everything we see seems to have originated at a point, a single point. Okay, and you can't really do physics with a point. Certainly can't write down a differential equation if you've only got one point. Okay, so that's the fundamental paradox, is how did everything come out of a point? The point, of course, is the Big Bang singularity. And so my work has been really geared towards understanding this. And what I claim is that when you understand this, you don't need that. Okay? You can just forget about inflation. It turns out to be completely unnecessary. Inflation was very important. It, as a real mathematical model or collection of models, it helped to make the case for observations. And if you read the papers of the Planck satellites, for example, you will find tens of inflation models there compared with the data. I think some of those scientists now believe that was probably a mistake to put so much modeling into a paper which is essentially observational. But anyway, that's what they did. All we see is what we call vanilla lambda cold dark matter, and I'll explain that in a moment. That's the basic phenomenological description of the universe that fits all observations so far, surprisingly well, and it's very simple. But so that's what you need to fit the observations. The inflation comes in an infinite number of varieties with ad hoc fields, parameters, and initial conditions, and so it's not a very satisfactory predictive science. There's no sign of a multiverse, quite the contrary. The further out we look, the simpler the universe appears. And then in detail, inflation predicted what we call tensor modes. These are gravitational waves, but of very long wavelength. And they would be created during this burst of exponential expansion. The gravitational waves would be fluctuating in their vacuum just by the Heisenberg uncertainty principle, and then this explosion of the universe would stretch them to very large scales with significant amplitude, and we should see them. There's no sign of them. Stephen Hawking made a bet with me that these would be seen by the Planck satellite, but as with most of Stephen Hawking's bets, he got it wrong, and they were not seen. The simplest model of inflation, called phi squared inflation, where you assume you have a free function to play with in inflation, essentially, and if you assume that function is quadratic, that's sort of a simplest case, has a minimum. This is now ruled out. So I'll just show you that. This is kind of interesting, that the tensor scalar ratio tells you what fraction of the fluctuations in the microwave sky, the ones I showed in that picture at 380,000 years old, what fraction of those fluctuations are due to scalar perturbations, namely just density perturbations, as compared to gravitational waves. Okay, so the fraction predicted by the theory depends on the details of this potential. Here's phi squared, up here, predicts about 15%, and the observations are down here. Okay, so there's now an upper bound on the fraction of anisotropy due to gravitational waves of about 3%, far lower than this theory predicts. And the exciting thing is that over the next 4 years, that bound is going to go down by about a factor of 10. Okay, so this pressure on simple inflation models is going down and down. If it ends up being less than 0.3%, inflation will be very implausible indeed. Now, I should say that inflation, I mentioned there's a free function. You can choose this function to avoid the bound, and you can keep dialing it down, but as you do, you just keep pushing yourself into a smaller and smaller corner of theory space. And in any case, as I mentioned, there's some other sort of fundamental problems that might make you worry about this theory. This picture is also useful because it shows the scalar tilt. Conventionally in cosmology, the spectral index for the scalar perturbations, 1 is counted as scale invariant. It's just a historical reason. So this would be perfect scale invariance. In other words, the same amplitude perturbations on all length scales. And what you see here is that the observed one is 0.9, just above 0.96. So there's a little bit of tilt here, and this is one of the parameters in the lambda CDM model. And as I'll explain later, we believe we now have a fundamental explanation for that number, the difference between 1 and what we see. Okay, so here's the lambda CDM model. It just has 5 free parameters. And as I say, it's very surprising. There's no evidence for anything beyond this in large-scale observations of the universe. And this is a very, you could say, the very disappointingly economical model of the large-scale universe. 5 fundamental physics parameters. The first 3 are to do with the energy content of the universe. So energy, of course, is in radiation. That's like the base level energy that came out of the Big Bang. Then there are baryons, protons and neutrons. And so there's a number here which tells you how many baryons per photon. It's about 10 to the minus 10. Then there's the amount of dark matter per baryon. We seem to have dark matter in the universe that doesn't couple to light. I'll give you an explanation. The simplest yet explanation for the dark matter will be coming soon in this talk. And then finally we have a cosmological constant, which now provides about 70% of all the energy in the universe. And the cosmological constant really is the simplest form of matter you could imagine. It's absolutely uniform in space, in time, and it's even invariant under Lorentz transformation. So if you move relative to the dark energy, it doesn't change at all. It's a very peculiar substance, but because it's the simplest form of matter, Einstein actually conjectured that this was important in cosmology around 1920, and he was right. It's amazing that he wrote down his equation for the simplest cosmology. He said, okay, I'll just assume the simplest form of energy, and then almost a century later it was measured, and indeed it is there. So there are 3 basic numbers for the energy, and 2 for the geometry. So here you see in this picture of the universe these small fluctuations that came out of the Big Bang. So the way we describe these fluctuations in the space-time geometry is typically with the Newtonian potential. This has a definition even in Einstein's theory. And the Newtonian gravitational potential, the RMS amplitude on it, on a wave number k, is approximately constant, but then has this small tilt. It's slightly stronger at longer wavelengths or smaller wave numbers. And so this is what came out of the Big Bang, where the amplitude is about 3 times 10 to the minus 5. And this directly translates by a famous formula into the temperature fluctuations you see on the sky, which are just 1/3 of the gravitational potential. I'm using speed of light equal to 1. And so 1/3 of this is that. And so the temperature of the universe is 3 degrees Kelvin, and the fluctuations on the sky are about 30 microkelvin. Okay, and this is what we measure when we look out to the microwave sky. The small tilt is about 0.02. It's something like a critical exponent, and I will explain that later in the talk. Very many quantities consistent with 0. Composition of the universe doesn't seem to change from place to place. As I say, no gravitational waves came out of the Big Bang, just scalar perturbations. The universe is spatially flat. It could have been curved, it could have been closed like a sphere, a 3-dimensional sphere, could have been open like a saddle, a 3-dimensional saddle. The curvature is 0, and many other parameters consistent with 0. So we live in an extremely simple universe, and the puzzle is to explain why. Why is it so simple? So here's a picture of the CMB anisotropy on large scales. This is, of course, the sphere which surrounds us, but projected onto this oval shape. And this is what's seen by the Planck satellite. I was very fortunate to get into this game when I was a young faculty member in Princeton, and people had calculated this temperature anisotropy. Jim Peebles, who won the Nobel Prize for this and many other contributions. So Jim Peebles had calculated this temperature curve, This is just the power in microkelvin squared. So you see 30 microkelvin squared is about 1,000. That's the amplitude at low multipoles. And then as you go up in multipoles, you see these beautiful oscillations. They're just due to acoustic waves in the plasma. The theoretical predictions were done in the 70s. The data lines up beautifully with them, provided I use those 5 parameters in the lambda CDM model. What we did in the 90s was to generalize this to polarization. The light coming from the Big Bang is partly polarized, and the number is quite small. So this is microkelvin squared again. So these are only, this would be less than 10 microkelvin. But we nevertheless calculated it. The beautiful thing about this curve is that there are no free parameters. If you fit the lambda CDM model to this curve, fit all the parameters, you just predict that. There are no free parameters. Okay, so the polarization we see on the sky is exactly what you'd get according to the laws of physics we know. So that's sort of disappointing at some level. We haven't learned anything, except that the laws we know we learned on Earth are actually apply everywhere. But this was my first kind of experience that, wow, things are really simple. You know, very few places in experimental physics where you get a curve like this, agreeing with the data. And it just happens this is on the largest scales we know of, and it fits perfectly. Okay, so this was an early indication that the universe indeed is extremely simple. Now let's go to the opposite length scales, very small scales, and it's actually the same story. So on small scales, people built, of course, accelerators, and they, the more powerful, the higher energy they went to, the more particles they discovered. The Standard Model was put together in the 70s and converged to this picture by the end of the 1970s. The Higgs boson of conjectured in the 1960s, the quarks, the leptons, the forces, strong, weak, and electroweak, gravity. And I've actually included in the Standard Model right-handed neutrinos because I define the Standard Model to be the minimal picture of fundamental physics which explains all the experimental data that we see. And this is enough. These right-handed neutrinos are necessary in order to explain the small masses we see neutrinos to have through neutrino oscillations. And the right-handed neutrinos are, as I'll explain in a moment, very naturally explain those tiny masses. So this is what I consider to be the Standard Model. And there's a huge volume of evidence in favor of it. Again, the same story as with the Planck satellite. When the Large Hadron Collider was built, most theorists like me were saying it's going to discover more particles. Okay, supersymmetry, there will be WIMPs, there will be, even some people said, small black holes. And so far, nothing. Okay, the Higgs boson was found, big success, and I owe my current position to that, the Higgs chair, but nothing else. So you might be very disappointed by that, but I think it's great because it might mean maybe this is all there is. Maybe these are all the laws of physics, and our job is actually to understand what they mean and why they are actually consistent as they are. So let me explain a little bit about right-handed neutrinos. In the Standard Model with only left-handed neutrinos, the neutrinos have to be massless. It's just inconsistent with the symmetry of the theory to write down a mass for a neutrino. So in the 1970s, people introduced right-handed neutrinos to explain the masses of neutrinos through the seesaw mechanism. And it's very intuitive, actually. The way it happens is the left and right neutrinos couple to the Higgs. And so the right-handed neutrino is very heavy. So if you send in a left-handed neutrino, which is very light, this neutrino has to be virtual. You just don't have enough energy to make a real right-handed neutrino. So what happens is it mixes a little bit quantum mechanically, and then discovers it's in an impossible state, and so it goes back to being a left-handed neutrino. So this is neutrino mixing. The right-handed neutrino is virtual. The heavier you make this one, the shorter the time you mix with it. Okay, just the uncertainty principle. And so the heavier this guy, the lighter the mass of the left-handed neutrino. So that's the seesaw mechanism. And what I'm going to explain to you now is that quite possibly one of these right-handed neutrinos is the dark matter. Okay, the dark matter puzzle is the most, probably one of the most famous puzzles in cosmology. What is the dark matter? Again, there are tens of thousands of candidates for dark matter, but I would claim that one solution has been staring us in the face since the 1970s, overlooked for a funny reason, which I'll explain, and it's just that it's one of these right-handed neutrinos. They're the perfect candidate because they don't couple to the forces in the Standard Model. Again, for symmetry reasons, they're not allowed to couple to these forces. They only couple to the Higgs and the left-handed neutrinos. And with a certain assumption, you can make one of them absolutely stable, and then it's the dark matter. So this is actually how we started off. Yes, everything couples to gravity. Yeah, you'll see in this picture, gravity encircles everything. Yeah, you can't avoid gravity. Okay, so how did we solve the dark matter puzzle? This is how we started thinking about the Big Bang, strangely enough. You see, and here's a little bit of mathematics. I'm generally avoiding mathematics in this talk, but here it's a little bit inevitable. The standard Big Bang, the right-hand side of this picture, has some remarkable mathematical properties. Namely, if you look at the metric for a space-time which is dominated by radiation near the Big Bang singularity, it looks surprisingly simple. Okay? Here's the space-time metric in suitable coordinates, and you see the size of the universe goes like t, the time. So as time goes to 0, the size is just shrinking away to 0. You square it because this is a length squared. So that's if you take a perfectly homogeneous universe, it would just be minus dt squared plus dx squared. Okay? But actually, there's a general class of solutions which are regular at t equals 0. And here you can have a three-metric, which is even in t, okay, and perfectly analytic at t equals 0. Analytic means there's no branch cut. The continuation through t equals 0 is unique. And so, and this has actually been known since the 60s, but wasn't appreciated what it meant. So actually you can go through the Big Bang singularity in a completely unambiguous way. So we noticed this and conjectured that the universe is consistent with what's called CPT symmetry. So CPT symmetry is the most fundamental symmetry we know of in quantum field theory: charge conjugation, parity, and time reversal. But the observed universe doesn't seem to be consistent with that, because time is going one way, we have more matter than antimatter, okay, and parity symmetry is broken too by the laws we see. But if the universe had this image universe before the Big Bang, actually it would be compatible with CPT symmetry. So this was our sort of formal argument that maybe there was a copy of the universe before the Big Bang, and we got it just by extrapolating the known laws through. Now, if that was the case, you see these right-handed neutrinos, this dark matter, nobody had proposed these right-handed neutrinos to be the dark matter for a very simple reason. The way we are used to calculating the abundance of particles is by assuming everything is in thermal equilibrium, right? That determines their abundance. And then you watch what happens as the universe cools and particles fall out of equilibrium. These right-handed neutrinos, if they only couple to gravity, were never in thermal equilibrium. So how do you calculate their abundance? So people said, well, we don't know how to calculate their abundance. Let's assume they're unstable, and then we won't have to worry about it. Okay? It's literally that's what happened. If, however, they are stable, and they were never in thermal equilibrium, it turns out you can calculate their abundance in this doubled universe picture because they are created by the time evolution of the metric itself. So, so you impose the CPT symmetry, it picks a particular vacuum state. In that vacuum state, it turns out there are, the right-handed neutrinos are produced essentially as Hawking radiation from the Big Bang. So I won't go through the maths of this, just tell you that the equations are completely well-defined. You can work out how many right-handed neutrinos there are, and they can be the dark matter. Now let me emphasize again that the size of the universe is this very simple function. The Big Bang was a simple 0, and we're actually extrapolating this scale factor back to negative t. And turns out in the future infinity, because we have the dark energy, this function a of t has a simple pole. So it's a very basic mathematical observation that the universe we live in came out of a simple 0 and is heading to a simple pole. Okay, and as soon as I use that language, you can tell I'm talking about complex analysis. And there's something even more remarkable, which is that this scale factor of the universe with realistic matter, radiation, dark energy, or cosmological constant, this is a doubly periodic function in the complex plane whose only singularities are simple poles. And furthermore, it's periodic in imaginary time. We'll come to that a little bit later. And that implies that the real universe has a Hawking temperature, like a black hole. So I won't go into any details of this dark matter solution, just to say you can solve the dark matter problem. It's a right-handed neutrino. And there is a prediction, which is if one of these right-handed neutrinos is stable, then one of the left-handed neutrinos is exactly massless. And you can see that from this picture. You see, this diagram shows the right-handed neutrino decaying. Right-handed neutrino goes into Higgs and left-handed neutrino. If you want it to be stable, you must switch off that vertex. You switch off that vertex by imposing a symmetry on the standard model. It makes this particle stable, but it also stops the left-handed neutrino mixing with it. And that means this particular left-handed neutrino is massless. And then, wonderfully, this prediction is actually going to be tested in the next 5 years by galaxy surveys. And that's a whole different story. I'm happy to talk about it if anybody's interested. But by observing the clustering of matter in today's universe, we're actually going to get limits on the mass of the neutrino, on the sum of the masses of the neutrino, and we will be able to test this hypothesis that the lightest one is massless. Okay, so let's go back to the Big Bang. The Big Bang is, in our picture, a CPT mirror. The boundary condition at the Big Bang is just like the boundary condition at a mirror. It's a perfectly reflecting boundary condition. So when you look back at the Big Bang, actually you're looking at yourself. Okay? You can, if you like, you can focus on one side of the universe and impose these boundary conditions, or you can think about the other side. The two are completely equivalent. And one way of saying it is that the pre-Bang universe is just the mirror image of the post-Bang universe. You're all familiar, I'm sure, with the method of images. You know, if I'm solving Maxwell's equations with a perfect mirror, I can actually impose that the tangential electric field is 0 on the mirror and so on. Or I can just say, no, I'll make if I'm right-handed, I'll make a left-handed copy of myself behind the mirror and throw the mirror away and solve Maxwell's equations, and it gives me the right answer. So that's essentially what this picture is, that the pre-Bang universe is just a mirror image of the post-Bang universe. So it's very economical, this picture. Okay, we're not adding any new phase before the universe. We're just imposing a boundary condition consistent with the most fundamental symmetry we know in physics, which is CPT. Now I'm going to talk a little bit about path integrals and gravity, because this is where another of Hawking's seminal ideas come in. I was very fortunate to overlap with Stephen at Cambridge and spent a long time with him and slowly absorbed some of his ideas. I think my current perspective is that he didn't realize how deep his insights were. Even he didn't, okay? He had very deep insights about gravity and quantum mechanics, but when inflation came along, he said, great, the perfect place for my ideas to really be used. But I now believe that his ideas are actually so powerful that you don't need the inflation. His ideas sort of do all the conceptual work for you. So path integrals and gravity. So here are all the laws we know of fundamental physics. Einstein's theory of gravity, Maxwell's theory, Yang-Mills, they all take the same form. Dirac's theory of particles, and then the Higgs contribution. And basically what these laws tell you is that every process in the universe is nothing but interference. Is nothing but interference. You just add up a phase, that's what this integral does. Add up phases, let things interfere quantum mechanically, and every natural process can be described this way. So this is a wonderful formula. It's a very difficult formula. It's probably the most oscillatory integral you could ever imagine. It's in very high dimensions, infinite dimensions, and this phase is wildly oscillating, and nobody knows if this integral even exists mathematically. For a recent attempt to define integrals like this, we have a recent paper. But nevertheless, it's a tremendously elegant formula. And so every physics experiment can be accounted for with this formula, at least a sort of particle physics type experiment, I should say. And with, now what Hawking realized is that the same formula can be used to calculate the partition function, which is the basic object in statistical physics. So essentially this formula is a matrix element of the time evolution operator, e to the minus iht. But if t is minus I beta, then that's the matrix element of e to the minus beta h, which is the Boltzmann factor. And so you can use this formula to get the partition function. What you do is take periodic boundary conditions in imaginary time, and then you look for a saddle point to this formula, which tells you the dominant Ford geometry, and the partition function is just the exponential of the gravitational entropy. So there's this tremendously elegant connection between the entropy of a space-time and the fundamental path integral formula for the amplitudes. And so Hawking used exactly this method to get the entropy of black holes. I think that's this picture. And it turns out that if you look at a black hole, so it has some classical space-time associated with it, there's a space-time metric, and the metric for a black hole turns out to be periodic in imaginary time. And that period is exactly the inverse of the Hawking temperature. So that was realized in the 70s, and Hawking and others used this to calculate the gravitational entropy. The gravitational entropy is nothing but the action for the theory calculated over one period in imaginary time. Now, let's come back to the puzzling large-scale geometry of the cosmos. So as I mentioned earlier, the universe is incredibly simple. The geometry of the universe on large scales is just flat space. You know, Euclid, it's exactly what Euclid would have guessed. X, Y, and Z, three-dimensional flat geometry. And this is a beautiful picture by Roger Penrose. He imagines the creator creating the universe, and for some weird reason, the creator chose to make the universe in this very special geometry. Flat, homogeneous, isotropic, and that's bizarre. This fact gets well, it seems bizarre because there's so many alternative geometries, you know, for the universe. Space could take any form, could be highly curved, black holes everywhere, but it's not. So now, prior to our work, the only work on the entropy of a cosmological space-time was de Sitter space. So de Sitter space is a space-time where you have nothing except a cosmological constant. Okay, so imagine I've got the simplest form of energy, and I solve Einstein's equations. This is what I get, at least if that energy is positive. This is what you get. So it's basically a contracting three-dimensional sphere, which contracts, bounces, and re-expands. To calculate its gravitational entropy, what do? Well, you go to imaginary time. You discover that the space in imaginary time is just a four-sphere. That's the most symmetric possible space. You then write down the Einstein action. It's an Einstein-Hilbert action. You calculate it for a four-sphere. It's a trivial calculation, and here's the entropy. For the observed value of the density of the dark energy or cosmological constant, you get 3.26 times 10 to the 122. So it's a huge number, the entropy of an empty universe with dark energy. For comparison of that number, the entropy of all the radiation in our Hubble volume, or our observable patch of the universe, is about 10 to the 90. So the gravitational entropy is substantially bigger than the entropy of the usual type, just the thermal energy in photons. So it's a very big number, so it's plausible that gravitational entropy actually dominates considerations of what is the most likely universe. So this is where things stood until a year or so ago. And then we realized we could calculate this gravitational entropy for a realistic universe. So how do we do it? Well, we take the line element with the scale factor. We assume that we assume conformal symmetry, which is essentially it's local scale invariance of the theory, like Maxwell's theory possesses, at the Big Bang. This means that although the universe has shrunk to a point from one perspective, from the perspective of the matter in the universe, if it's like photons, like radiation, it doesn't know about the size of the universe. The photon doesn't know the size of the universe. The photon just stretches with the expansion of the universe. But you can look at the system in a different set of variables. We're just taking out that stretching, and the photon behaves exactly as if the universe was not expanding at all. Okay, so there's a special symmetry which comes in, and which is related to this analyticity of the metric. Anyhow, so we look at these equations. Here is the Friedmann equation. It tells you how the scale factor of the universe evolves. If you have radiation, matter, we allowed space curvature. We wanted to see how this affects the entropy, and dark energy, the cosmological constant. I've just ignored all numerical factors. Now, when you write it in this form and you think about it, you see what you want to do is study this equation in imaginary time, and then you want to calculate the entropy by integrating around a closed loop in imaginary time. So that sounds impossibly difficult until you realize this is nothing but a particle in a quartic potential, and the solution for that has been known for well over 100 years. Okay, and it's well known to have very beautiful properties. There are functions called Jacobi elliptic functions, which are the general solution of such an equation. And it was known for well over 100 years that these are periodic in imaginary time. Okay, but this was overlooked until a year ago. These analytical properties are really beautiful. So we found the exact general solution to the Einstein equations. These solutions determine the Hawking temperature and the gravitational entropy. So if you look at the real part of A of t and the imaginary part of A of t, and you plot them in the complex t plane, you find there's a fundamental domain, which is a rectangle in general, and with its opposite sides identified, and then the whole complex plane is just tiled with these rectangles. So in fact, this function lives on a torus. You identify the opposite edges of the rectangle. The function lives on a torus, and there's a non-contractible loop around this torus, which is the red curve, and the action calculated on that red curve doesn't matter on the details of the curve. It just depends on the topology of the curve, how many times it goes round. And so the action is a topological invariant, and that's the entropy of the space-time. Okay? So obviously I'm only giving you a very brief glimpse of this, but I hope you get the impression this is really very elegant stuff. And this is exactly what Hawking anticipated, except he didn't realize that the solution of this was a simple analytic function. It's periodic in imaginary time, etc. In fact, in the imaginary time picture, which is more like thermodynamics, the universe is this completely finite object. Now, I say that because we have assumed that space is finite. Okay, either it's a three-sphere, if it's positively curved, which is compact. If it is negatively curved or flat, we have put in boundary conditions which make it periodic in order just to keep our formulae finite. None of what I say depends on the details of that. So it's just like studying the system in a box. And with those, given that space is a box, essentially, then the universe in this imaginary time is just a finite object, and you can study this thing, right? And to compute anything in today's universe, what you do is you analytically continue in time. So there's this sort of static picture of the universe, and we're a sort of real-time image of it. So we recently showed that this gravitational entropy favors a homogeneous, isotropic, and spatially flat universe, and a small positive cosmological constant. So both those things are exactly in agreement with what we see today. So people are still sort of struggling to make sense of this calculation, but the maths of it is completely uncontroversial. The meaning of it is another matter, okay? And if you take it at face value, it says we know why the universe is so simple. It's just because it maximizes the gravitational entropy. Just like where the air in this room is uniform, right? Not because anybody had a mechanism for smearing it out. It's just because the most microstates are uniform. And that's the same for the universe. So if this explanation is right, there is no need for any mechanism to explain these properties of the universe. They're just the completely obvious ones determined by thermodynamics. So there was this nice illustration in Quantum magazine that if you were to pick a universe at random, what would it look like? And that's essentially what we're doing. Pick a universe at random, and most of them will look like ours. Now, I'm going to get on to the fluctuations. And because of time, I'm going to, let's see, have I got 10 minutes? Is that all right? Okay. So I'm solving all the problems of the universe in 1 hour. Okay. So I'm actually amazed I'm on time. I'll try not to slow down. We have to explain those fluctuations we saw in the sky. Why is the universe not completely uniform? Right? The previous calculation of the entropy actually favors uniformity. Just like the thermodynamics tells you that the gas in this room is approximately uniform, or uniform to a very high accuracy. So the previous calculations actually favor uniformity. Where did the non-uniformity come from? So I think there's one idea in inflation that is worth keeping, and it's that quantum mechanics somehow played a role. Okay, so the idea is, quantum mechanics tells you that this is what the vacuum looks like. Every field we know of, the electromagnetic field, the Higgs field, the electron field, they're all fluctuating in the vacuum. There's nothing you can do to stop those. It's Heisenberg uncertainty principle. That should be your picture of the vacuum. It's just like harmonic oscillator. It doesn't sit at zero. It's got a Gaussian wave function in its ground state. So this is what fields are doing in the vacuum. The vacuum is a very interesting place. Now, when you study a quantum field, you have infinitely many harmonic oscillators, okay, and you add up their vacuum energy and pressure, and it's infinite. So the vacuum is a crazy place, which has infinite energy density and infinite pressure. Turns out bosons give you plus infinity, and fermions minus infinity. Now, to get a picture of this infinity, I mean, you should be troubled. How on earth can we couple gravity to fields like electromagnetism if they have infinite energy in the vacuum? The whole universe is going to collapse immediately, right? Something is wrong. The point is that particle physics and fundamental physics has literally been avoiding this problem for a long time. We use something called renormalization. And renormalization allows you to subtract infinities. I mean, that's why it was invented. And so using renormalization, you can just ignore this, but it is a physical fact that these vacuum fluctuations are infinitely wild on short distances, and we know of no way to avoid that. In fact, this is one of the motivations for string theory. String theory, it was hoped, would be a finite theory in which everything was finite. Now, a better picture of this vacuum is, I won't dwell on this, but basically there's a nice regularization you can adopt. You can say, so smooth out the fluctuations by saying I'm only sensitive to a certain range of energies. I can't go up to infinite energy. That corresponds to smoothing things on a certain time scale. And then you discover what's in the vacuum is really radiation. These ultraviolet fluctuations have an equation of state of radiation. And so it even breaks Lorentz invariance. If you try to look at this physically, you would find that the vacuum is not even Lorentz invariant. So something is deeply wrong in quantum field theory, coupled to gravity. Gravity is the only thing that cares about this, by the way. No other forces coupled to the stress energy. So we don't have a physical picture of the quantum field vacuum. There are even worse thing about these divergences called Weyl anomalies. Maxwell theory, as I've already implied, Maxwell theory is invariant under local changes of scale. And you know this very well because a radio wave is the same as an X-ray, is the same as a photon of light, obeys exactly the same equation. And that's telling you that the equations have a symmetry. If you change the length scale, the equations are invariant. And you can even change it locally. You can, stretch space here and shrink it over there, and the equations are still identical. So these anomalies in that symmetry means those symmetries are broken by this wild quantum behavior. And those cannot be removed by renormalization. So there are sort of sicknesses in our description of quantum field theory which seem to be very deep. So I'll tell you, I don't have much time to tell you, but essentially we discovered a new way to cancel those sicknesses. Okay? And they involve rather strange set of fields which have an action, instead of being grad phi squared, which would be something like the Higgs field, it's box phi squared. 4 derivatives in the action. Okay, this sort of breaks the standard tradition that in physics we only have 2 derivative equations. We introduce 4 derivatives. You can see it's kind of nice because now there are 4 derivatives to go with the 4 powers of x in the integral, which is telling you that this field doesn't have any dimensions. We call it dimension 0 field. I won't dwell on this, but to say the reason I started out interested in this field is because it has scale invariant. You see, it's dimensionless. So if you Fourier transform its correlation function, it has to be dimensionless. So there's d3k over k cubed. That's scale invariant. So such a field looks like exactly what we see in the microwave background. Okay, it's a dimensionless field with the right spectrum to explain what we see. That was the initial motivation for even looking at these fields. What we found is that the vacuum energy and these Weyl anomalies can all be cancelled by these funny fields. And they're very funny fields because they don't have any particles. Okay, they only have one physical state, and it's the vacuum. So it's a peculiar field theory with only one state, which is the vacuum, but vacuum's all we need. So you add up the energy, half h bar omega for every Fourier mode, dimension 1 scalars, fermions, like in the standard model, the quarks and leptons, the gauge fields, and these dimension 0 scalars. And then you get these Weyl anomalies. They're just sums of integers, right? So with peculiar coefficients. And then we know how many of these fields there are. Number of gauge fields is the dimension of the gauge group, which is 12. In order for all 3 sums of integers, positive integers, to cancel, you have to have the number of fermions be 4 times the number of gauge bosons, which is 48. That happens exactly if there are 3 generations of particles in the standard model. Okay, so these 3 problems in coupling to gravity all cancel if and only if you have 3 families of elementary particles. Okay, it's, as far as I know, it's easily the simplest explanation for why there are 3 families. And the number of these funny fields is 36. And we don't know why the 36 comes about. There are some ideas, but we don't know. It requires 3 generations. It also requires that the Higgs is rather sad, because I hold the Higgs chair. But if this mechanism is true, then there cannot be a fundamental Higgs field. Okay. So this mechanism only works if the Higgs field isn't a fundamental field. The Higgs field is a composite built of other fields. But that's a nice idea anyway, because the Higgs scale is much lower than the Planck scale. So then, last topic I'm going to tell you about is, I think, most exciting, which is an explanation of the cosmological perturbations. So I've kind of motivated these dimension 0 fields by saying they improve the standard model's coupling to gravity. Do they actually give us density variations, coming out of the Big Bang? So here we are today. We're looking back at the Big Bang 14 billion years ago. If we take our current observable region, 20 gigaparsecs across, and scale it back to the Planck temperature, it's about 10 microns across. Okay? And the 1 millimeter scale we see today, that's roughly the wavelength of the microwave photons. If we scale that back to the Planck temperature, then we get the Planck length, and the ratio between these two is about 1 to 10 to the 30. So when we want to explain the large-scale structure of the universe, we need to explain the form of the fluctuations at the Big Bang, literally at the Big Bang, over this huge range of scales, 10 to the 30. So our claim is that we can do that, okay, using these dimension 0 fields. And tomorrow I'll give a technical talk where I'll explain this in much more detail, but I just want to give you an impression now. So here are the couplings in the standard model G3 is the SU3 gauge coupling, G2 SU2, G1 the U1 Y. And the main feature you see is that this coupling gets weaker as you go to higher energies. Okay? And it's perfectly finite at the Planck scale, right? The G3 is about 0.4 at the Planck energy. So this is called asymptotic freedom. It says that as you go to higher energies, QCD becomes weaker. Well, if something becomes weaker as you go to short distances, does that remind you of anything? It should remind you of the tilt. The tilt says the fluctuations get stronger as you go to large distances, slightly. Okay? And so what we now claim is that that variation is exactly what we see in the CMB. Okay, here's the formula. So I'm not giving the derivation, I'll give it tomorrow. Here's the power spectrum. This is essentially the Newtonian potential. There's some numbers here, 2 pi's, etc. This is all a direct consequence of the standard model and this conformal symmetry. These are all calculable in terms of the standard model couplings. Number of degrees of freedom in the standard model, that's just counting all the particles. And then there's this tilt. And that number epsilon I told you about, which was 0.02 in the RMS, this is the power spectrum, so it's the square of the RMS. But that 0.02 squared, when you square the amplitude to get the power spectrum, becomes 0.04. It turns out 0.04 is just 7 alpha 3 over pi. Okay? And where alpha 3 is the QCD coupling at the Planck scale. And people ask, what's the 7? Where did that come from? And particle physicists know this very well. This comes into the QCD beta function. It's 11 minus 2/3 times the number of flavors. Number of flavors is 6, and so 11 minus 4 is 7. Okay, and so that's the explanation for the tilt on large scale. So there's an algebra to go through, but here's the upshot. The predicted spectral index is 0.958, and the observed one is 0.959. Okay, and then the amplitude, and a priori, our calculation could have given any number from 1 to infinity, okay, but it comes out to be about 10 to the minus 9, which is within a factor of 2 of the Planck satellite. Okay, so it's very remarkable. Maybe this is a coincidence. Coincidences often happen, and we focus on them when they're successful. So maybe we're completely biased, okay? But I can assure you we didn't finagle anything here. We did an honest calculation, and we were very surprised that the answer came out so close. There's a vast extrapolation, 30 orders of magnitude in length scale, but actually that's completely justified if the Big Bang was a essentially statistical mechanics system, and this number is a critical exponent or scaling dimension. Essentially, that dependence on scale is just dimensional analysis. And that holds over any length scale, right? 10 to the 30 is fine, it should still hold. Yeah, I could mention this asymptotic safety. There's some other ideas about gravity. So just to summarize, we've solved the solutions, we found the solutions of the Einstein equations, used them to make a picture of the Big Bang, calculated the gravitational entropy, there are new explanations for these basic puzzles, and these funny fields, which have fields but no particles, can do wonderful things for us in cosmology. So this is an extremely minimal picture of the Big Bang, very encouraging, but lots remains to be understood. So thank you.
Thank you very much, Niels, for this very thought-provoking talk. We have time for a few questions, maybe. Anyone? Yeah, in the back. Maybe you want to? Maybe you shout. Yeah.
Okay. Yeah. Thanks for an interesting talk.
Thank you.
So I was wondering about the vacuum energy and your calculation there.
Yeah.
So first, maybe to the observation of the violation of the Lorentz invariance in the results. So
Yes.
You introduced a Lorentz violating regulator? And then
No.
surprising that the result was
I didn't do that.
Okay, good.
I'm stealing this entirely from this review, so Bryce DeWitt is really one of the people who thought most deeply about quantum fields in curved spacetime. And I think in his whole career he wrote 6 articles, and each one is an absolute masterpiece, okay? So he really formulated the subject. And so the point here is you don't want to break Lorentz invariance. The usual way people present the vacuum energy, what do? They write integral d4k, and they integrate from 0 to lambda. And they say, oh, there's lambda to the 4th. That completely breaks all relevant symmetries. It's a ridiculous calculation, okay? So DeWitt was much cleverer than that. He said, no, you see the T mu nu is typically quadratic in the field, even for a free field. It's quadratic, right? So you've got these 2 fields. So take your 2 fields at separated points and use the separation as the regulator. All right? So the whole calculation of Lorentz invariant. So the answer is going to depend on the proper separation between the 2 points. That's all. And you take it to be time-like separated, because then the time-like length is inverse with the energy uncertainty. So the time-like separation is essentially a smoothing scale over energy. So if I take it separated by delta t, proper time-like separation, then I would only be counting energies up to h bar over delta t. Okay, so as I send h bar delta t to 0, I'm counting all the energies, all possible energies. So it's a Lorentz invariant regulator, which he's using, and this is the result. Okay, so what he's doing is smoothing over very high energies using a proper Lorentz invariant regulator. And what DeWitt does in his article is much more than this. He considers parallel plates, and he tries to compute what's the force of attraction due to vacuum fluctuations between 2 parallel plates. And he points out that if you do the calculation in a conformal invariant theory like Maxwell, you get a sensible answer. But if you do it in a non-conformal invariant theory, like people typically use, then actually you get ridiculous answers. Okay, where the stress energy is divergent between the plates and not even integrable. The integral of the function of x is divergent. So it's a beautiful discussion of this whole problem, which does give you a very physical picture of what these fluctuations are doing. And, you know, they're pretty bad.
I think we had a... Yeah, go ahead.
So you started out talking about maybe this, we complicate our theory to explain the simple universe.
Yeah.
And like add all these fields.
Yes.
But to someone who's not, and I'm sure there's an explanation for this, but these 36 zero-dimensional fields, aren't they the same kind of thing?
They are. You're absolutely right to call me to task for that. My only excuse is they don't have any particles. So I'm not adding any particles. All these things are doing, as far as we currently understand, all they are doing is shifting around the vacuum. Okay, so whereas the vacuum in the standard model without them is wild and out of control, when we add them, it makes it behave nicely. So that the stress test is traceless, the vacuum energy is 0. One hopes that makes the theory more finite. So when you do now calculations with gravity, typically we get divergences, but if you remove these kind of 0th order problems, and I emphasize this calculation we've done is really 0th order. These are free fields. We're not including any interactions. So it's absolutely 0th order calculation, lowest approximation. If you've kind of improved the theory at 0th order, you hope it's going to be better at higher orders, but nobody knows. So yes, you're absolutely right. I'm throwing stuff in. But notice so far there are no free parameters here. And if you come to my talk tomorrow, you'll see that when we calculate the fluctuations, there are no free parameters either. Okay, so I'm doing everything I can to keep the theory economical, principled, and predictive.
Sasha?
Since you mentioned that Higgs is unplausible,
Yes.
it's the same quantum numbers as before, but what is made of now?
Yes, so we don't know is the answer, but there are some guesses. So for example, if you take a right-handed neutrino, multiplied by a left-handed neutrino, that actually has the quantum numbers of the Higgs, right? Obviously there was that vertex, so there is a model of a composite Higgs due to Chris Hill, which is, I think he wrote a paper called "The Higgs is Made of Neutrinos." And that might work here, but we need to figure out what these funny fields do in terms of potentially binding the neutrinos together to make the Higgs. You know, if you made such a theory, it would be very attractive because it would solve the hierarchy problem. Well, you hope it would solve the hierarchy problem. Explain why the weak scale is so much smaller than the Planck scale. Now, in fact, if you ask why were all these people interested, you see the people who studied this funny theory goes back to Heisenberg, 1957. He called it the dipole ghost. And then Pauli wrote a paper about it. Thirin, Nakanishi, you know, it's been lurking in the literature. Why were they interested? Well, at least some of them, because this theory gives a linear potential for phi. The static potential for phi in 3 dimensions is linear, and they thought this may somehow be a phenomenological model of confinement and composite particles. Yeah.
Isn't it a matter of semantic then that the phi itself, the black matter candidate?
No, phi. Well, it could be, but it behaves completely differently to the dark matter. This theory, if you look at how phi behaves in the universe, you see there's only the vacuum, okay? But if I put a classical phi field in the universe, it behaves like Maxwell theory. This theory is conformal invariant, so it doesn't see the expansion of the universe. It's nothing like dark matter.
So we have time for a couple of questions. So we have Hans.
So thank you very much for a very interesting talk.
Thank you.
Now, this is a question that is presumably slightly a little bit beyond, because it's more about the standard model than cosmology, but
Yes.
you touched on both subjects. Do you have any ideas about the mass hierarchies that people have spent lots of time, after all, I mean, motivation for introducing many of these complications were to understand
Absolutely.
hierarchies, and perhaps also
Absolutely.
the strong CP problem.
So the strong CP problem, we do have something to say about that. This mirror image universe, it's, as you can see, there's a kind of time reversal symmetry here. And we've written a paper about that. It's more Latham's work than mine. So I'm not going to explain it very expertly. But basically, one solution to the strong CP problem that has been proposed is that the fundamental theory is left-right symmetric. And so that was parity, using parity symmetry. And then this left-right symmetry gets broken. And people argued that that in itself would solve the strong CP problem. People like Larry Hall and Harigaya have written papers to that effect. So what we did is just simply generalize their work to having time reversal symmetry. And we say, if the theory has this time reversal mirror symmetry, that itself would remove the FF dual term, the strong CP problem. So I don't claim it's a final answer, but it's, we have a paper on it. It's very detailed. And the fundamental assumption that the state of the universe is CPT symmetric, we relate to a solution of the strong CP. If you have T symmetry and CP symmetry, T symmetry and CPT symmetry, then you obviously have CP symmetry. So we've tried to relate it to those. The other questions about the hierarchy puzzle, we're just beginning. There are some papers based on our paper which attempt to build explicit models of the Higgs and of fermion mass matrices. I haven't studied them in detail, so I would say it's early days. But you know, the most important message of this lecture, I would say, is not that we've solved everything, but it's that there may be things lurking. There may be simpler solutions lurking in the literature, including the old literature, which people have overlooked. And people have rushed for these hyper-complicated solutions like the multiverse and string theory and extra dimensions. But actually, in my view, it's very likely that the real solutions have been overlooked.
Great, let's see, we have, yeah, running out of time, so Darcy, please. Yeah.
So going back to the beginning of the talk, you were giving an argument for why right-handed neutrinos could be dark matter. You gave an argument for why the abundances could match up, but was there a reason you'd expect them to be cold?
Yes. So when you do this calculation of the production of right-handed neutrinos across the Big Bang, and you match the abundance of dark matter, you exactly determine the mass of the right-handed neutrino. And it turns out it's 5 times 10 to the 8 GeV. Okay, so it is what it is. It's right or wrong. If it's 5 times 10 to the 8 GeV, it's absolutely cold. And so, yeah, you can calculate. Essentially, roughly, it is produced when the Hubble constant equals 5 times 10 to the 8 GeV. That's when it's generated as Hawking radiation. And ever since then, so at that time it would be relativistic, and ever since then its momentum has been redshifting away. So it's absolutely cold dark matter. There are some other predictions of the theory that they relate to neutrinoless double beta decay. We predict exactly what the rate should be, but it turns out that rate is as small as it possibly could be, and so the experiments will take at least a couple of decades to reach that. So there are predictions, but they're minimal ones. And in cosmology, we predict that the sum of the light neutrino masses should be 60 millielectron volts. That's the minimum allowed by the observed mass differences. I should say that's assuming the normal hierarchy. The inverted hierarchy, I think it's 110 millielectron volt, and that's probably going to be ruled out first. So if all this makes sense, then one could expect that in something like 5 years' time, we will see that the sum of the light neutrinos, let's say, is 60 plus or minus 10 is reasonable expectation. Our prediction is 60, and we might have measurements accurate enough to plus or minus 10 millielectron volts. That's dependent on a lot of modeling of clustering under gravity and so on. But the Euclid satellite is launching in June, and that is the expectation value of the expectation of the team working on neutrino masses. So I think if it reached that point, we will, well, in my view, this will become easily the most likely candidate for the dark matter. Now, I don't think people should abandon all the other dark matter searches, because it may still be wrong. And our prediction is very minimal. You know, we're basically saying a number is 0. So people should still keep looking for other dark matter candidates, but I think this will be the best motivated one.
All right, thank you, Neil. I think Neil will be giving a more technical talk perhaps tomorrow afternoon, 1:30, so save remaining questions for that talk. But for now, let's thank you again for a great talk.